Hey everybody, how are you doing today? Hope everybody is safe and well. We're going to move into 1.6 in the Math 71 program. And even though this section is part of Chapter 1 and it's considered review, and much of it is, I believe there are going to be some elements in this section that you would not have seen in Math 51, or maybe you would not have just seen in your past. So we're going to take a look at it. And what 1.6 is dealing with is properties of integral exponents. Integral comes from the word integer. So the exponents on these exponential expressions that we're going to be looking at in 1.6 are integer exponents. The exponent might be 0. The exponent might be any natural number, 1, 2, 3, 4, 5, to infinity, and the opposites of those natural numbers, -1, -2, -3. So the exponents can be positive, they can be negative, they can be 0. They are integral exponents that we're going to be dealing with. And I'm going to categorize these various rules of exponents that we're going to be looking at in 1.6 by capital letters. So let's begin. Capital letter A, rule number 1, product rule of exponents. Very much review, but I'll share the proof anyways. Let's say we're given two powers that are going to be multiplied together. Notice their bases are the same. 3 to the second times 3 to the fourth. Let's kind of show a proof. This is merely a proof. 3 to the second means 3 times 3. I brought down the major time sign there. 3 to the fourth means 3 times 3 times 3 times 3. If I were to count the total number of times that the base factor of 3 occurs, 2 times there, 4 times there, it occurs a total of 6 times. Therefore, our answer would appear to be 3 to the 6th. I'm not concerned about what its numerical value is. I am concerned that you look at the original problem and you, so to speak, kind of follow the flow chart arrow. Notice, being that the answer is 3 to the 6th, how could we have come up with 3 to the 6th without doing any of this? Well, it doesn't take an Einstein. If we bring down one of our like bases and take the two exponents and add them together, 2 plus 4, that just happens to generate that 6 as well, and that's not a coincidence. That is the rule. So the rule for the product rule of exponents says this: if A does not equal 0, A to the m times A to the n will always equal A to the m plus n. Those threes, they represent A. There's the m, there's the n. If we bring down an A, if we bring down the 3 and add the m and the n together, we'll get our answer of 3 to the 6th. That is the product rule of exponents. I'm going to share 3. There's a reason for each one of them. Number 1, 5 to the 4th times 5 times 5 to the 6th. Maybe a couple of reasons. One reason, the middle factor of 5 does not visibly show its exponent, but you and I both know that it's 1, so I'll just go ahead and insert it. Does that mean you have to? No, you don't. But we have to account for that one factor of 5. The other reason why it's up here, there are from time to time careless mistakes made in the fact that some people will literally multiply those bases together. The 5 times the 5 times the 5, and that is not what the product rule of exponents says. The product rule says, as long as you are multiplying powers that have the same base, you bring over one of those bases. And you take your exponents and you add them up, and I'm going to save a little bit of time here. We're going to add right from here. 4 plus 1 is 5. 5 added to 6 to the 11th. Done. Number 2. There's a reason as well for this. Negative 3n to the second multiplied by a negative 5n to the third. If you wanted to just compute out, multiply those two factors together and write the answer down, we would not discount you. It's a pretty elementary problem. But I do want to share that we can make use of properties to really solidify a good answer and not make some sort of a careless mistake. I put an equal sign and I formed two groups. Inside group number 1, I'm going to insert the two coefficients of these two little exponential expressions. I'm going to insert negative 3 times negative 5. And in the second house, I'm going to put the powers of n. N to the second times n to the third. Now, we're going to eliminate those groupings by multiplying. Negative times negative, that gives us a 15. N to the second times n to the third, add those exponents, n to the fifth, 15n to the fifth, done. Final answer. Again, do you have to show the associative and commutative properties? Do you have to show the groupings? No, you don't. You could go right to that if you can without any issue. Just remember, careless mistakes do come about. Now I'm going to erase this right here because the bottom one is going to require maybe just a little bit more room. And I want to make sure that I've got that room for it. Now on the third one, you can view it right now. I'm not going to read the entire problem. It's 3 factors that are going to be multiplied together. And you can see a couple of those coefficients of factors are rational numbers. And for that reason, I believe it's wise to make use of the commutative property of multiplication and the associative property of multiplication and form groups. Because I think careless mistakes can be made if we just attempt to go after this problem and think that we can just immediately write down the answer. Many of you possibly can, but I'm going to share this. I'm going to form 4 different groups. Group number 1 is going to form with the coefficients of those 3 factors. House number 2 will be for the powers of A. House number 3 will be for the powers of B. And house number 4 will be for the powers of C. So I'm going to start it right up here. And let's put in those coefficients first. Negative 2/3 times 15/8 times negative 12, which we'll write negative 12 over 1. House number 2, the powers of A. A to the second times A to the first times A to the second. House number 3, B to the first times B to the fourth times B to the sixth. And house number 4, the powers of C. C cubed times C squared times C to the first. Now let's come back to the very first grouping. And the first thing that I would do, there are 3 factors up there. 2 of them are negative. An even number of negative factors will always promote a positive answer. So I just might note that the sign of my coefficient is going to be positive, and just jot that down. Now I don't have to worry about the signs. Now, for the sake of space and time, I'm not going to prime factor anything. We'll cross cancel. The 3 will cross cancel with the 12. 3 goes into itself once, it divides into 12 4 times. 2 cross cancels with 8. 2 goes into itself once and into 8 4. And then finally, these 4s right here will cancel to 1s. And if we look at everything here, all we have is a 15 times 1. So we have a positive 15. And now the rest is the product rule. Bring down the common base of A, add the exponents to the 5th. Bring down the B right next to it, add the exponents, I believe to the 11th. Bring down the C, add the exponents, that's to the 6th. Done. Yes, I'm a firm believer of the groupings. I believe it will pay off when we do that. Okay? That's the product rule. Let's go to B, and let's go to the quotient rule. The quotient rule of exponents obviously has to do with division. What happens if we are dividing with 2 powers that happen to have the same base? Well, obviously, it'll give us a straight up rule. But let's prove it. A to the 7th would mean A times A times A times A times A times A times A, divided by A to the 4th, 4 factors of A. Now, if we cancel, where we can cancel 1 pair of A's, replace them by 1s, a second pair, replaced by 1s, a third pair, replaced by 1s, and a fourth pair, replaced by 1s. And you can see that all the factors of A in the denominator have canceled out, just leaving us a 1. And in the numerator, there are 3 remaining factors of A, which if we write exponentially, we'll have an answer of A to the 3rd. Doesn't take much now to look at the original problem and its answer and see that if we subtract the exponents, the exponent in the denominator from the exponent in the numerator, we also happen to get A to the 3rd. And that is the quotient rule of exponents. If A does not equal 0, A cannot be equal to 0 for this quotient rule of exponents to work. A must be non-zero. If A does not equal 0, quotient rule says A to the m divided by A to the n will always be equal to A to the m minus n. Let's look at just a couple of quick little examples. I'll kind of write it over here. Number 1, negative 18m to the 5th n to the 4th divided by 9m squared n. I'm not going to break it up into sections. I don't believe it's necessary. Not at this point. Start with the coefficients, divide. Negative 18 divided by 9. Negative 2. Go now to the quotient rule of exponents with the m's. M to the 5th divided by m to the 2nd. If we subtract the top exponent by the bottom exponent, 5 minus 2, m to the 3rd. N to the 4th divided by n to the 1. 4 minus 1, that's n to the 3rd as well. Done. Number 2. I believe I might split this one up because when we look at the initial factors of negative 16 in the numerator and 20 in the denominator, we're looking at a rational number. We're not looking at a situation that we saw in number 1. So I believe I would intentionally split it up and make number 2 maybe begin to look something like this. Negative 16 over 20 times the quantity of x plus y to the 5th divided by the quantity of x plus y to the 4th. And now let's begin with this fraction, negative 16 over 20. Again, I'm not going to show prime factorization. Everybody in the room should be able to see that the greatest common factor for 16 and 20 should be 4. It definitely has to be negative. 4 will divide into 16 4 times, and 4 into 20 will go 5. So we've got a negative 4/5. And now the quotient rule. Our bases are the same. We bring down one of those bases right next to that negative 4/5. And when we bring down one of those bases, you're going to have to keep that x plus y in the house. Just keep it in the house. And now subtract the exponents. 5 minus 4 is 1. You can put a 1 up there or just leave the answer in this way. And if some of you are thinking, would I need to distribute that out on number 2? You do not. That is not necessary to do. Okay. That is letter B. And now we're going to go to letter C. And I want to transfer this paper over. Okay, let's go to C. Rule of 0 exponents. What happens when the exponent is 0? That's what we're going to be talking about. Here's our proof. We're going to use an expression that is like the one that we just came from, whereby we'll use the quotient rule of exponents to sort of prove this out. 2 to the 4th divided by 2 to the 4th. Now, folks, keep in mind, what I'm showing you right here is a proof. You're not going to be writing all of this stuff down when you actually are following through on this rule. This is a proof that's going to lead to a rule. We're going to have to do 2 things with this problem. 2 to the 4th divided by 2 to the 4th. The first thing, with the arrow drawn to the right, I'm going to simplify this problem using the quotient rule of exponents. Letter B that we had just done. Why can I use it? Because I'm dividing with powers that have the same base. Bring over one of those 2's. Take the exponent on top, 4, subtracted by the exponent on the bottom, 4. We get 2 to the 0. Now, assuming that we're talking to an audience or a group of people that they realize that that answer is 2 to the 0, which I boxed off, let's assume that we don't know what that value represents. Let's just assume that we don't know what its evaluation would be. That's not true, but let's just assume. Now we're going to have to do this problem in another way to point out what that 2 to the 0 in fact does mean. I'm going to take that numerator power of 2 to the 4th and I'm going to write out its meaning. It means we're going to repeat the base of 2 4 times. 2 times 2 times 2 times 2. The denominator, likewise. 2 times 2 times 2 times 2. We cancel out where we can, and we can cancel everything. That first pair of 2's factor to 1's. 1's, 1's, 1's. We have a 1 on top, over a 1 on the bottom, and 1 divided by 1, 1. Now, if we got 2 to the 0 as an answer using the quotient rule, And we got an answer of 1 when we wrote out the meanings of the numerator and the denominator, and they're both true statements, then the following must be true. 2 to the 0 must mean the same thing as 1. They must be equal to each other, and they are. The rule of zero exponents says this: if a does not equal 0, a cannot be equal to 0. A to the 0 exponent value will always be equal to 1. Now, holding on to this theme right here for a moment, the only thing that a can't be is 0, because 0 to the 0 would not be 1, it would be 0. But a can be any positive number, or a can be any negative number. And it doesn't matter what kind of real number, positive or negative. Every non-zero base of a taken to the 0 power will always be equal to 1. Now we're going to take a look at a few examples of the rule of zero exponents, and there's a reason for each and every one that I'm going to do. And we'll just start with this one, basic. Well, we'll just start with him. No work. Our a value is 9. He isn't 0. He happens to be a positive 9. Every non-zero base taken to the 0, no work, 1. Number 2. -9 to the 0. This time our base is clearly negative. That's our a. Doesn't matter what the sign of a is, positive or negative. -9 to the 0, ditto. Now as we go down the lineup, got to be a little bit careful. A bit of a difference. Notice there is no parenthesis around the -9 like we saw on number 2. And when there is no parenthesis seen, that means the 0 exponent is only applying to the 9, not this negative sign. The only way that that 0 could apply to the -9, as you might read this to be, is if the -9 were in a house. So we're going to write out its meaning first before we actually evaluate this. This negative sign is not part of your base of 9 because it would have had to have been parenthesized for it to be. That negative sign, one of its interpretations would mean it's the implied sign of an imaginary factor of -1. And that's how I'm going to look at this. That negative sign really is meaning -1 times 9 to the 0. That's what that really means. Well, then if we bring down that -1 and the times sign, 9 to the 0, that's 1. And -1 times +1, -1 would be the final answer for that. So one of the reasons for putting problem number 3 up there is, just because you see an exponent of 0, that doesn't necessarily mean that your answer is going to be 1. In this case, it was -1. Let's go to a fourth. M to the 5th times m to the -5th. If we apply the product rule of exponents, rule A that we initially started off with, if we bring over one of those m's and add the exponents, 5 added to a negative 5, m to the 0, we are going to assume that m cannot be equal to 0. We will assume that, and an instruction will tell you that. Therefore, if m cannot be equal to 0, then it must be a non-zero value, and any non-zero value taken to the 0, 1. Kind of erase. And let's go to number 5. Maybe a trifle different. The quantity of negative 6m to the 0. As long as m is non-zero, that means m would have to either be some positive number or some negative number. Let's just test it a little bit so we can really see why the answer is going to be what it is. Let's say the value of m is 2. That would then get it down to the quantity of negative 12 to the 0, and every non-zero base taken to the 0 power would be 1. So if the value of m is positive, we get it down to this. That answer certainly would be equal to 1. Let's say the value of m is negative. Let's say m is negative 2. Then negative 6 times negative 2 would be a positive 12, and 12 to the 0, that would be 1. So from the get-go, you don't have to do any of this. As long as we know that m cannot be equal to 0, it does not matter whether m would be a positive value or a negative value, because all of it is tucked inside this house. Everything is inside the house. Everything inside the house is your base, and any non-zero base taken to the 0, 1. Really no work. I just showed a little bit to point out some things, but really no work. But now we go to number 6, and it just changes slightly, and it goes to this. Like you know, that 0 is only referring to its base of m. He's not part of the base. He's just a coefficient factor. Down. M to the 0, 1. Negative 6. Just a little different. 7. No big thing, but I'm just trying to cover base here. Here's our non-zero base. He just happens to be a rational number. Doesn't matter whether he's positive or negative. To the 0, 1. And then finally maybe this one. And then we'll close off this one. The quantity of 7t to the 0 minus 6t to the 0. Well, we already pointed out this term right here in a prior example. As long as t does not equal 0, it doesn't matter what the value of t is. It can be positive or negative. It doesn't matter whether the overall answer inside here would be positive or negative. Any positive or negative outcome to the 0, 1. Bring down that minus sign or that subtraction sign. And just like a previous example, that 6 comes down. It's not part of the base. That 6 will get multiplied by the value of t to the 0, which is 1. Little order of operations, 1, negative 6, negative 5, done. So folks, that's a glimpse and some examples of the rule of 0 exponents. Let's go to D. All right, folks. We're going to move into letter D of the rules of exponents. But just one parting comment on Rule C, the rule of zero exponents. Just remember this. Zero exponents are not allowed for an answer. They're not permitted. So the rule of zero exponents says any non-zero base taken to the zero power is 1. So 1 is the simplified answer. 2 to the 0 is not. That's not permitted. All right, let's go to D. It's the rule of negative exponents. Now, to show the rule of negative exponents, we're going to show a proof that is similar in structure to the rule of zero exponents that we just came from. And here's the problem that we're going to look at and use as our proof. 3 to the second divided by 3 to the fifth. I'm going to do 2 items, 2 things to show the rule. Over on this side where the arrows are pointing, we're going to use the quotient rule of exponents. We're dividing with powers that have the same base. So I'm going to bring over that common base of 3. We're going to take the exponent on the top and subtract it by the exponent on the bottom. And we know that 2 minus 5 will then give us 3 to the negative third. So that is an answer that we obtained by using the quotient rule of exponents. And notice, it has a negative exponent. Question would be, what does he mean? What does he mean? Well, we're going to find out what it means as we go to the other form of the proof of this same problem, using factors. The numerator, 3 to the second, means 3 times 3. The denominator, 3 to the fifth, means what you see right there. I'm going to cancel as many factors of 3 as I can. We can do one pair, replaced by ones. We can do a second pair, replaced by ones. We end up with an answer of 1 times 1 for our numerator, which is 1, and 3 times 3 times 3, written exponentially, 3 to the third. Box that one off. Notice this answer up here has a negative exponent in it, and this answer down here does not. Let me give you this statement right now before we go further into this proof. Negative exponents are not permitted. Just like an answer taken to the zero power is not permitted, an answer with a negative exponent is not permitted. So we can't accept 3 to the negative third. We're going to have to accept 1 over 3 to the third. And now I want us to take a look at both of these statements right here. They are equivalent to one another. They're equal to one another. They have the same value to one another. But this is the accepted one. That's not. Now I want us to take a look at this situation and see if we can kind of see something that this rule of negative exponents is going to tell us. I want to do this first. I'm going to cover up the negative exponent of this first answer that we got. I'm just going to cover it up. And I'm going to cover up the exponent that happens to be positive in the accepted answer. I'm just going to cover that up. I want you to look at these remaining numbers that are inside each of these respective boxes. If I were to ask you right now, what is the relationship between 3 and 1 over 3? Pretty common mathematical word. No, it doesn't have anything to do with opposites. It has everything to do with the fact of reciprocals. The relationship between 3 and 1 over 3, they're reciprocals of one another. Because remember, this 3 that's right up there actually would mean 3 over 1. If we take 3 over 1 and invert it, or reciprocate it, we'll get 1 over 3. So one key item that the rule of negative exponents tells us is the bases are reciprocals of one another. This base had the negative exponent. This one had the positive. So here's the first step that we follow when we're changing a power that has a negative exponent to an equivalent expression that has a positive exponent. Step number 1. You change the base to its reciprocal. So if we take this base of 3 and change it to its reciprocal, we'll get 1 over 3. And step number 2, you simply change the negative exponent, the negative 3, to its opposite, a positive 3. And you have the preferred model that we want. Let me share a parting comment, a truth, before we look at some examples. Negative exponents lead to reciprocals. Negative exponents lead to reciprocals. Where does it begin? You take the base, you change it to its reciprocal. That then gives you the authority to change that negative exponent to its opposite, positive 3. By the way, for this answer right here, we would not leave this necessarily as 1 over 3 to the third. We would simplify that 3 to the third in that denominator, and we would call it this. That would be our final answer. But that's the answer that I wanted to leave it as, so I could generate the proof behind this. So now we're going to take a look at a total of 5 little problems that deal exclusively with the rule of negative exponents, and we'll start with number 1. This puppy is just like him. Step number 1. Change the base to its reciprocal. Remember, that 5 is actually that. Invert it, reciprocate it. And then step 2, change that negative 2 to its opposite. And because this is very easy to further simplify, we would write 1 over 25, a done deal. Number 2. That negative 4 is actually negative 4 over 1. And notice that negative 4 is in a house. So when we reciprocate it, we'll keep it in its house. Reciprocate that, and we'll have this. We'll have that. Actually, we could just write it like this. I could leave it that way, but let's just do this. When we reciprocate that, will become 1 over negative 4. We'll just write it like this. Keep that negative 4 in the house. That gives us the authority to change that negative 3 to a positive 3. And since negative 4 to the third power is a very reachable simplification that we can do, the 1 will stay on the top, and negative 4 to the third would become negative 4. times negative 4 times negative 4. When you look at this, there's an odd number of negatives, so that's going to make the answer negative. 4 times 4 is 16, and 16 times 4 will make that a negative 1 over 64. It can be written like that. You don't need to change it. It can stay like that. If you want to take that negative sign and put it even Steven with the fraction bar, you can do it. If you want to put the negative sign up there by the 1, you can do it as well. We'll just leave it in that way. It's fine. Now up here I decided to include like a number 3 before I went to that 4 and 5. I want us to look at that number 3. I don't want you to be confused. We have a power with a negative exponent. Step 1, change the base to its reciprocal. So we reciprocate it. That gives us the authority now to change that negative 2 to a positive 2. And now let's simplify that. We're going to be sharing this rule a little bit later on. It'll be the last rule of exponents that we cover, but instead of having to write down 8/5 times 8/5 to get the overall simplified answer, we can begin by taking the numerator of 8 and taking it to the second power, and then go to the denominator and take it to the second power, and you are done. Okay. Now, let's just add a little oregano. 3x to the negative 6th, y to the 4th. He's not changing. He's not changing. He is. Now we'll do it in stages. I'm going to bring down that 3. And I might just write it like this. I don't need to, but I will. Put a times sign. X to the negative 6th. That can't stay that way. We're going to have to make use of the rule of negative exponents. Take the base, change it to its reciprocal. Remember that's x over 1. Flip it, and we'll have 1 over x. Now we have the authority to change that to a positive 6. Then a times sign. Leave him as he is. We'll just write him over 1 as well. So notice he was the only one that we applied the rule of negative exponents to because the others had positive exponents. Now let's multiply across. 3 times 1 times y to the 4th. 3y to the 4th over x to the 6th. And you see, folks, everybody is happy because there's no longer negative exponents in our answer. Number 5. Be careful. That negative sign is not affiliated with this base. The only way that negative sign would be a part of that base is if that negative, along with the 6, were tucked inside of a house. It's not. That negative 3 exponent is applying to the base of 6. Not him. So we begin by making this negative sign an implied negative 1, like we had shared in a prior example. So I'm going to bring down a negative 1. And I just might put him over 1. I'll bring down a times sign. Now we're going to apply the rule of negative exponents for this 6 to the negative 3rd. Flip the 6 over 1. Flip that 6 to its reciprocal. Then that gives us the authority to change it to the 3rd. Leave the a to the 2nd alone. Just when you bring it down, just maybe you want to put it over a 1. B to the negative 1st, he's not good. Reciprocate that b. Then that gives us the right to change that from a negative 1 to a positive 1. I can put that positive 1 there, or I can just leave it b on the bottom. One last time sign. Got to change it. Reciprocate that C. And then it'll go to the fourth. Now let's put this package together. The sign of the overall answer is going to have to be negative. You can keep it up here by the numerator. You can put it down here by the denominator. You can put it even Steven with the bar. And a lot of textbooks would do just that. Most textbooks would never put it down there by the denominator. You could, but they won't. We'll just keep it even Steven. Now let's multiply across and we have an a squared. And on the bottom, we have 6 to the third, which I believe a textbook would simplify it further down. That's 36 times 6, and that'll give 216. B, C to the fourth. And you don't need any more of that, and that would take care of that. So those are some examples that specifically deal with the rule of negative exponents. Now, there's an appendage to letter D that we want to take a look at. This that I'm putting up is still part of D. It's the rule of negative exponents, or it's an addendum to the rule of negative exponents, where negative exponents appear in the terms of fractions. And I'm going to get this erased right here so we have the room to do the examples when we get to that particular point. Now, this addendum right here to letter D, I don't think this would have been discussed in Math 51 necessarily. It's exclusively 71, I believe. Negative exponents appearing in the terms of fractions. And when I say in the terms of fractions, I'm implying the numerator term, the denominator term. So here's the little problem that we're going to show a proof of that's going to lead to a further rule that we can follow when this occurs. When the numerator or the denominator or both numerator and denominator contain powers with negative exponents. Negative exponents appearing in the terms of fractions. What I'm about to show you right here is going to lead to a rule for this kind of expression. You're not going to be writing all of this when you actually do your exercises, but this is being done to give you a reason for this rule that you'll see right down here. So let's start this flow chart in this way. 3 to the negative second divided by 5 to the negative third. Now very carefully, I'm following the arrow. I put my fraction bar. I took this numerator term of 3 to the negative second and I used the rule of negative exponents. I reciprocated the 3, 1 over 3, and I changed the negative 2 to a positive 2. I did the same thing with the denominator. 5 to the negative third, reciprocated the 5, 1 over 5, authority to change the negative 3 to a positive 3. So this statement is equivalent to this one. One thing going for it is no more negatives, exponents. Now we're going to rewrite this division statement. You see, this is not only a fraction bar, but it's a division symbol. We're going to rewrite this division statement in another equivalent division statement using the division symbol that we work with when we're dealing with fractions. So I wrote 1 over 3 to the second first. I changed this division symbol fraction bar to the division symbol that we use when we're dividing with fractions. And then I wrote 1 over 5 to the third. So this is equivalent to the prior statement. Now that division statement over there, I'm going to use the rule of division. Just like when we're dividing fractions. The 1 over 3 to the second remains the same. Took the division sign, changed it to multiplication. Then took the second fraction over there, that 1 over 5 cubed, and reciprocated it. 5 to the third over 1. And then multiply across 1 times 5 to the third, 5 to the third, 3 to the second times 1, 3 to the second. Folks, first truth. These two statements that are boxed off, they equal each other. We have honored everything in a truthful way. 3 to the negative second over 5 to the negative third is equal to 5 to the third over 3 to the second. Notice the statement on the left contains negative exponents. The statement on the right contains positive exponents. We cannot accept him. We must accept the guy on the right. Let's look at that equation for a moment and see what we might be able to gather from this equation. Notice this 3 to the negative second, this numerator term that's on this left-hand side. If I take its base and I switch it to the other side of the fraction bar. If I take this base, which is in the numerator position, and I switch it to the other side of the fraction bar and place it in the denominator position, I'm not changing the sign of the base. If I switch this base to the other side of the fraction bar, that will then give me the authority to change its negative exponent to its opposite. And likewise here, if I switch this base of 5, it's in the denominator position right now. If I switch this base of 5 to the other side of the fraction bar, elevate it up, put it up there in the numerator position, that gives me the authority to change that negative 3 to a positive 3. That would be the accepted answer. What is the rule that we can follow when we are working with fractions that contain negative exponents either in the numerator or the denominator, or both the numerator and the denominator? The key word, I believe, is switch. And here's the rule. When you switch the base to the other side of the fraction bar, the exponent changes to its opposite. So when you look at this immediate problem right up here, we're not going through all of that. That was shown, that was done to show a proof. We're going to follow this rule. So I'm going to show it right here, and then we'll do others. He is no good. He cannot be negative 2 as an exponent. So because he's in a numerator position, we're going to take this 3, and we're going to switch it to the other side of the fraction bar. Down to the denominator. That gives us the authority to change that negative 2 to a positive 2. This puppy, he's no good. He's not accepted. We're going to change this base. We're not going to change it. We're going to switch it. We're going to switch this base from the denominator position to the numerator position. And we did. And that gives us the authority to change that -3 to a +3. Now let's look at a few. Number 1. That's no good. Bring down a brand new bar. We're going to have to switch because he's a negative exponent. Switch this base to the other side of the bar. Gives the authority to make him a +2. This puppy. Negative exponent. He can't stay there. Switch this base to the other side. Change. Now let's simplify. 4 times 4 times 4. Yes. Yes. Done. An elementary problem, but a key one. Let's go to 2. Nothing is wrong with him. He's not going anywhere. This guy, he can't stay that way. Now, just for a moment, I'll bring down a bar. We really don't need it, but I'll bring it down. We've already got a 1 here. We're going to switch this base up to the numerator. Sometimes I use the expression, we're going to put him on an elevator and send him up a floor. We're going to move him up. Don't change the sign of that base. Don't change that sign. We're just going to switch this base to the other side. Don't change the sign of that base to a +3. It doesn't say change the base. It says switch the base. Switch the base to the other side. Change the sign of that exponent. We really don't need the fraction bar. We've got 1 times a -3 to the second. That would be 1 times 9, 9. 2. Let's go to 3. He stays. Here. That -2 has no relationship with that 5. He only has a relationship with his base. The 5 stays down. X to the -2nd. Don't have to go up. Switch that base to the other side. Gives us the authority to make him to the 2nd. You can leave the answer like that. You could also erase the 1. A textbook answer would erase the 1, and there would be that answer. It's 3. 2 more. Let's go to 4. It's quick. A to the -3rd, B to the 5th, over C to the -4th. Bar. Any item that already has a positive exponent, he's staying. Items that have a negative exponent, they're going to be switched. This guy. Switch this base to the other side. Gives us the authority to change him to the 3rd. The B to the 5th, he's going to stay right where he's at. Let's go down here, the C to the 4th. He can't stay on the bottom. He's going to have to move up to the numerator. Switch that base to the other side. Change him to a positive 4. We'll put a close actually on letter D by looking at this guy right here. It's a little lengthy, but basic. Negative 24. A squared. B to the negative 2nd. C to the 8th. Over negative 8. A to the negative 5th. B to the negative 1st, C to the 12th. Well, this is a negative divided by a negative, and that's going to change to positive. So I'm just going to kind of note that right here. They've been taken care of. 24 divided by 8. You see, the 24 is not carrying a negative exponent, and neither is the 8. So we'll just outright divide those. That takes care of those. Now let's go to our letters. Now you have the option, if you want to here, you can use the quotient rule of exponents here. You can use it here. And you can use it there. But I don't believe I would at this point. I believe I would accept this as a fraction, and I would get things switched as they need to switch. So let's just start with this numerator right here. Let's just go one step at a time. This A to the 2nd, he's going to stay right where he's at. Right, I'll just kind of scribble him out right now. Let's go to this fella. That B to the negative 2nd, he's going to have to move. So we're going to switch this base to the other side. And I'm going to put him maybe right about here. I could put him anywhere just as long as I bring him down in the denominator. And he'll become to the 2nd. Get rid of him. That's C to the 8th for right now. I'm just going to put him and leave him alone right there. A to the negative 5th. He's going to have to come up. So we'll elevate that A, we'll move and switch that A to the other side. And he'll become then to the 5th. That B to the negative 1st, he's going to have to be changed and moved up. I'll squeeze him right here. And I'll go ahead and pull a 1 there. He's been taken care of. And then that C to the 12th is going to stay right where he's at. Now, one thing that we've got going with us right here, one reason why I guess I elected to go this way, there's no longer any negative exponents that we're going to get bothered by. We're just going to have to be very careful as we simplify this. So I'm going to bring down a bar. Start off with that 3. We don't have any powers of A in the denominator, so we're going to multiply the A to the 2nd times the A to the 5th. We're going to add those exponents, because that's the product rule. And now, folks, we want to be careful with the B's and with the C's, so take a look at this carefully. We have one factor of B in the numerator, and we have 2 factors of B in the denominator. This one factor of B in the numerator will cancel with one of these factors of B in the denominator, and I'll still be left with one factor of B in the denominator. What else can we do? If we take the exponent on the bottom and subtract it by the exponent on the top, we'll be left with one factor of B left over, which is going to remain on the bottom because there are more factors of B on the bottom than there were on the top. And The same with the powers of c. We have 8 factors of c in the numerator and 12 factors of c in the denominator. There are more factors of c in the denominator than there are in the numerator. If you subtract 8 from 12, you'll get a c to the 4th. And that c to the 4th is going downstairs because there's more of them in the denominator than there are in the numerator. And we'll have that given answer. Would that have been the only way? It would not have been the only way, but it's a good way. That would be our given answer. So we're going to close the section off right here with that particular one, and in the next video we'll put together the last section of exponent rules that we need to do. Take care.